Section 8. Okay, we've talked about the basics of how samples approximate populations and how statistics estimate parameters. Now we want to go into a little bit more mathematical detail. Specifically, we want to look at the situation where we have yeses and nos as our individuals. In a word, categorical data. People who may or may not be left-handed, coins that may or may not be landing heads, things along those lines. We've talked about a lot of this before in Section 5, but now we want to kind of put it all together. So let's recap what we know from the previous sections. When you take a simple random sample from a population, populations, of course, are much, much larger than samples. And then you get a number from that sample. That's the statistic. A statistic from a simple random sample is a random variable. In other words, you have done something random. You have picked out people or things from a population, or you have repeated something theoretically random so many times, like flipping a coin. And in one way or another, you've gotten a number from that sample. So you've done something random and you've gotten a number. A statistic is a random variable. And like any random variable, a statistic has a shape to its randomness, what it's likely to be, a probability distribution, that is, and it has a center to its randomness, that is, the mean of that random variable, and it has a spread to its randomness, that is, the standard deviation of that random variable. Theoretically, the statistic from the simple random sample should be near the corresponding parameter. 11% of the people you looked at were left-handed, therefore probably around 11% of everybody is left-handed. But the reality is there are no guarantees, right? You could flip a coin, you could flip a fair coin 100 times and get nothing but heads. You could pick out 100 people and get all left-handed people through some cosmic quirk. Not because of bad picking, but simply because of the luck of the draw. So even under ideal conditions, if it's a simple random sample, we've talked about that as an ideal way of picking things, even under ideal conditions, there are no guarantees, and you could get almost anything. That's the point, you know, the sample is negligible compared to the population, so the sample in theory could consist of pretty much anything. All blue-eyed people, all left-handed people, and so forth and so on. It probably won't. It probably will be, quote, representative of the population, but there are no guarantees. Because it is random, we have to have rules for its randomness. The sampling distribution of the statistic, that is to say, the pattern that plays out for every possible example of that statistic, every possible group of 100 people, etc., etc., is exactly the same thing, or if you like, is just an alternate perspective on the probability distribution of the statistic. If 10% of samples will result in an average height less than whatever, then there's a 10% chance that the sample you're going to pick will result in an average height less than whatever. In the end, it's the same thing, right? That's what probability is. The probability of something happening is the proportion of times it would happen in the long run. The probability of our sample that we're about to do being this, that, or the other is just the proportion of all possible samples for which it would be this, that, or the other. That's simply what probability is. Sampling distribution of statistic, probability distribution of the statistic. How all possible examples of the statistic play out into a pattern, what the actual sample you're likely to do is likely to be. They're just two perspectives on the same idea. So for example, just a brief recap of the example we did in the last section, or something similar. Suppose we pick a simple random sample of people from the United States. Do you like action movies? Let's say it's 2,500 people. Let X be the number of yeses, and let P hat be the proportion of yeses. So X could be 0 or 1 or 2 or 3 or 4 or 2499 or 2,500. That is, it can be hundreds of things between 0 and 2,500. And if we divide by 2500, that's just a unit change, right? So this could be 0 over 2500, or 1 over 2500, or 2499 over 2500, or 2500 over 2500. X can be hundreds of different things between 0 and 2500. P hat likewise can be hundreds of different things between 0 and 1. Technically, they're discrete random variables. There's a finite number of things you can get, but for all practical intents and purposes, they're continuous. X can be effectively anything between 0 and 2500, in the sense that it can be so many things that we've lost all interest in whether it's this one or the next. And likewise, p hat can essentially be pretty much anything between 0 and 1. So in this case, we have p is our parameter, and p hat is our statistic. We've talked about this before, but now let's focus a little bit more on the notations. So for the purposes of this section, we'll let x represent the number of successes you get in your sample, and we'll let p hat, divide by the total, represent the proportion of successes you get in your sample. Those are our two statistics. X and p hat are both statistics, or rather say they're alternate perspectives on the same statistic. They're both random variables, and they have different but related probability rules. Now remember, if we go from one perspective to the other by multiplying or dividing by 2500, then we're going to do the same thing to the means and the standard deviations. We'll talk about that a bit later. So the bottom line, and by the way, notice again that if you divide every number by 2500, then you compress the shape of its distribution, but you don't really change it. Unit changes don't really change the shape of what's going on. We've seen this over and over, right? So the bottom line is if you understand one of these variables, you pretty much understand the other. They're alternative perspectives on the same situation. The number of successes is a little easier to look at because the numbers are not so microscopically small, of course. But the proportion of successes for the long run is the more useful statistic. I'll show you what I mean. If I take a sample of a lot of people from New York State, and 783 of them are left-handed, then I have absolutely no context for that, right? X is 783 left-handed people. Well, out of how many? You see, I've got to divide by the total before I have any context on that. If it's 783 over 1,000, or it's 783 over 10,000, I've got to divide by the total anyway in order to have some perspective on it. If I take a sample of a lot of people and 783 of them are left-handed, that's a useless piece of information, right? But if I take a sample of a lot of people and 11% of them, or 0.11 proportion of them, are left-handed, then I immediately know something, right? So that's the unfortunate thing, is that while the numbers may not be quite so microscopically small for counts, for proportions, they're going to be more useful. So for the long run, the proportion is the useful perspective. But for our immediate future, we're not going to be forming any real conclusions along those lines yet. That's future sections. For the immediate future, suffice to say that they're just unit changes. They're just alternate perspectives on the same situation. So if you understand one, you basically understand the other. It's a chart with 2,501 columns, probability of 0, probability of 1, probability of 2, or if you prefer, probability of this, and so on and so on. But it's close enough to say that they are discrete, that they are continuous random variables. They're effectively continuous. They're not perfectly smooth. It's 2,501 bars forming a pattern, but that's pretty smooth, right? It's essentially true to say that they can be anything between smallest and biggest, and exactly anything is pretty negligible, right? The tallest bar is still microscopically thin, right? So the probability of exactly anything is pretty slim, which you can't say for a sample of size 5, for instance. And I don't think I mentioned this, but here it is. We'll let P in this section represent the parameter. So Remember, hat, as I said, is a symbol that means estimator of. So p hat is our estimator of p. P hat is shooting for p. P hat will probably be close to p, and so forth and so on. So p hat is the statistic, the proportion of successes in the population. P is the parameter. P hat is the statistic, the proportion of successes in the sample. P is the parameter, the proportion of successes in the population. P hat estimates P. Samples estimate populations. And I'm not going to bother with counts for the population because, like I said, populations are too big to really even have counts. For all practical intents and purposes, when you're picking 2,500 people, there may as well be an infinite number of people in the United States, or an infinite number of all possible coin flips, etc. Populations are too big. So, like I said, for the long run, counts are not going to be very handy. And because you've got to divide out by the totals to compare them anyway, you may as well talk about proportions when things get practical. So, a lot of this we've already talked about. I just kind of want to recap it. Suppose that 60% of the population of the United States would say yes. So the proportion of yeses out there is 0.6. That's our P. Since 2,500 is so much smaller than the hundreds of millions in the population, it doesn't really matter if taking out that 2,500 is with replacement or without replacement. Taking 2,499 people away who do like action movies or who don't like action movies or anything in between is taking away approximately nothing, right? It's still approximately true to say that 0.6 is the proportion of people out there who like action movies. So it's effectively true. I mean, 0.599999, whatever. But it's effectively true that every time we pick, we have a 0.6 chance of a yes and a 0.4 chance of a no. And it's effectively true that they're independent picks, that taking away a few left-handed people, even 2,499 of them, is not really changing the rules when you go to pick that last one. With replacement, without replacement, it doesn't really matter when what you're picking is so small compared to what you're picking from. And don't forget, that's why we're doing it in the first place, right? If you could ask everybody in the United States whether they like action movies, or a quarter of them, or a tenth of them, it wouldn't be that much harder to ask everybody. But you can't, of course. So we never have to worry about this. Effectively, we have the same rules the first time we pick, the second time we pick, the last time we pick, because what we're picking is so negligible compared to what's out there. Otherwise, again, we'd simply just ask everyone and eliminate the randomness. We can't do that. The sample is a manageable size, a size we can cope with. Even if it's 2,500, the entire population is not. You can ask 2,500 people whether they like action movies. You can't ask hundreds of millions. And that makes a very big difference, remember. Statistic, parameter. So if you've been paying attention, you'll see that this example, and indeed a lot of the examples we've talked about in previous sections, are examples of the same basic situation, which I want to talk about here in point number 2. So point number 1 is a brief recap, just pulling together everything we've been talking about in previous sections. We're talking about the same stuff we did in section 7, but now we're going to put a little bit more math behind it, and we're focusing a little bit more on the idea that a statistic is a random variable, and thus can be quantified, described, understood, the same way that we did in section 5. So we have what we call the binomial situation. Suppose that we're in this following situation. Suppose that we have a fixed number of observations. We know how many times we're going to pick something or do something. We know how many times we're going to spin the spinner. We know how many times we're going to flip the coin. We know how many people we're going to pick out to ask them whether they're left-handed or like action movies or whatever. We know how many times we're going to pick or do something. Call it lowercase n. Fixed number of observations, call it lowercase n. Every one of those observations is a success or a failure. That is, it falls into one of two categories. There's nothing pejorative about failure. It's just that we'll call a success the thing that we happen to be more focused upon at the time. Being left-handed or not. Having blue eyes or not. Coin landing heads or not. People liking action movies or not. Whichever of the two categories we have our attention focused upon, we'll call a success, and the other one will be a failure. And point 3, the probability of a success is the same for each. You've got the same probability that the first one is a success, as the second one is a success, as the third one is a success, and so on and so on and so on. In other words, each pick is independent of the other picks. Regardless of what has gone before, the probability of success is always the same. Or in the real world, close enough, as we said. So every time we flip the fair coin, we've got a 1/2 chance of a head, and it doesn't matter what you've piled up behind you. Independent. Every time you pick somebody, you've got a 20% chance they've got blue eyes, and it doesn't matter what you piled up behind you, because there's so many more out there you can pick from. Every time you pick, there's a 0.6 chance that the person likes action movies, and it doesn't really matter what you've piled up behind you, because it's so negligible compared to the hundreds of millions out there. Every time you roll the die, there's a 1/6 chance of a 1. Every time you spin that 0 to 4 spinner, there's a 1/2 chance that it's less than 2, and so forth and so on and so on. Notice that calls in an awful lot of very different scenarios, but we have the same perspective in each of them. We're going to do something n times. We know how many that is. Every time you do it, you either get something or you don't get something. And the probability of getting that something is the same each time. Call that probability P. So notice that, again, P can be thought of as the probability that the next one is a success, or it can be thought of as the proportion of successes out there. It's exactly the same thing. Parameter, rules, governing principles, broader realities. Nothing to do with what you actually get. So, there's times when it's handy to look at it one way, and there's times when it's handy to look at it the other way. If you're tossing a fair coin, you would probably say there's a 1/2 chance of a head, rather than saying 1/2 of all possible tosses is a head. But if you're in a scenario like the above, you'd probably say that 0.6 is the proportion of yeses out there, rather than say there's a 0.6 chance of picking a yes. It's always the same thing. P for probability, P for parameter. Governing principles, broader realities. The rules. Let's see, what am I saying here? Note that this situation can either be using the same rules each time or picking many times from a much larger population. Yes, we've made this point many times before, right? It doesn't really matter whether you're doing something theoretical where it's exactly the same every time over and over, like flipping a coin or spinning a spinner, or whether you are just picking hundreds from a population of millions. You can flip the coin 1,000 times and you're never going to make a dent in all possible coin flips. But by the same token, you can pick 1,000 people from the United States and you're never going to make a dent in the population of the United States. It doesn't matter whether you're talking about a theoretical probability scenario or whether you're actually picking from a much larger population. The only sense in which it matters is that 100 coin flips you're about to do are philosophically interchangeable with any other 100 coin flips you're about to do. But when you're actually picking real things from a real population, we do have that messy idea of how you're picking and bias and all of that. We will always assume we're talking about a simple random sample, so that any 2,500 people you could pick has got the same chance of being picked, for instance. And that will take care of that problem. Because remember, a simple random sample eliminates the possibility of bias, and we will get back to that. So in this section, let's let random this is what they call the binomial situation. So let's let random variable x represent the number of successes we get when we follow these rules. then we say that, well, random variable x has a probability distribution, right? Like any random variable, section 5, it has a shape to its randomness. In toto, right? The chart. Probability 0, probability of x being 0. 1, probability of x being 1. 2, probability of x being 2, and so on and so on and so on. Whether it's 4 columns because you're going to flip a coin 3 times, or whether it's 2,501 columns because you're going to pick 2,500 people who may or may not like action movies. I'm not saying you necessarily want to think about something with 2,501 columns, but the point is in the back of your mind you could, It's the totality of its probability distribution, numerically in the chart, visually in the shape that you generate. And we've generated a lot of those shapes, right? Just to be different, we did some in the highlights section. Let's use the blue-eyed example again, So probability distribution, sample of size 1, sample of size 2. People who may or may not have blue eyes when you pick 2. In chart numerical form, in picture form. People who may or may not have blue eyes when you pick 3. In chart form, in picture form. Probability distribution, shape of its randomness. The point is, in this type of situation where we're following these rules, not all of the examples we did in section 5 were examples of these rules. We did some weirder things as well, like a couple has children until they get a boy or 3 girls, whichever comes first. Not everything is an example of these rules, but a lot of them were. So when you're talking about following these rules, then we have an abbreviation for the totality of this randomness, the shape, the picture. And that abbreviation is called the binomial distribution. So in other words, there is a word to describe this type of pattern of randomness. The number of yeses you get when you're going to do something n times, every one of those is a success or a failure, a yes or a no, and the probability of a yes is always the same. Say again, you're going to do something n times, every one you pick is a yes or a no, and the probability of a yes is always the same. Call it P. Then the number of yeses you get, that distribution of randomness, is called the binomial distribution, and it can be abbreviated capital B N, P. Different books will have their own abbreviations, but I think this is short and to the point. Notice, by the way, that this plays out a little bit differently from our space, not underscore, but you get the idea. This plays out a little bit differently from our capital N notation. With our normal capital N notation, the first blank was the mean, and the second blank is the standard deviation. In this notation, the first blank represents how many times the B represents that we're obeying these general rules. The N represents the number of times we're going to pick or do something. And the P represents the probability of a success, which is the same every time. Examples. Suppose you flip a fair coin 3 times. Then the number of heads you get is capital B 3, 0.5. Let's blow this down a little bit. So you're going to flip a fair coin 3 times. Well, yes, we know how many times we're going to flip it. Each is a head or it's not. The probability of a head is always a half because it's a fair coin. So the number of heads, the abbreviation for that binomial distribution is capital B 3, 0.5. Or while we're here, let's take a look at this one. We're going to pick 3 people. The probability that somebody has blue eyes was, 0.2? And that's the same every time. And, number 3, that is the same every time. And every time you pick, they have blue eyes, and they don't. So we obey those binomial rules. So the shorthand notation for this probability distribution, or this one, it's the same thing, is capital B, the number of people with blue eyes, X, is capital B 3, 0.2, I believe it was, yeah, probability of blue eyes. Capital B 3, 0.2. capital B 3 comma 0.4, and so on and so on. Capital B 80, sorry, what did I do there? Let's start from the beginning. Capital B 1 comma 0.2, capital B 2 comma 0.2, capital B 3 comma 0.2, capital B 4 comma 0.2, capital B 80 comma 0.2. Do you literally see where we're going with this, by the way? Thought of as individual bars, this thing is very complicated. On the other hand, it may look very familiar. And of course, the other examples that we did in the actual video, which was what? Left-handedness. So 0.1 chance that somebody is left-handed. Well, let's start from the beginning. We're going to pick so many people. They may or may not be left-handed. The probability of being left-handed is always 0.1, regardless of what you piled up behind you. And then we're talking about the number of people who are left-handed. So, yes, we're good to go. These are all binomial distributions. Capital B 1 comma 0.1, capital B 2 comma 0.1, capital B 3 comma 0.1, capital B 4 comma 0.1, which as far as we went, right? So whether it's in chart form, whether it is in chart form, or whether it's in picture form, the abbreviation for this pattern of randomness is that it is capital B 4 comma 0.1, 4 comma 0.1. Oh, and by the way, once you understand that this is capital B 4 comma 0.1, then it really doesn't matter whether you're talking about picking people who have a 10% chance of being left-handed, or rolling a crooked die that has a 10% chance of coming up the color red, or flipping a coin which has a crooked coin which has a 10% chance of coming up heads, or picking people who have a 10% chance of having green eyes, or any other scenario, right? We've boiled it down with that notation to its raw essentials. You're going to pick 4 times. Every time you pick, you've got the same probability of a success. That probability is 0.1. So we've taken the real world out of it and boiled it down to just the mathematics. More examples. Roll a fair die 80 times, or 80 fair dice is the same thing. The number of ones is binomial 80 comma 1/6, right? You're going to do something 80 times. Every time you do it, it's a 1 or it's not a 1. Let me be clear on that. Every time you roll the die, it lands O-N-E or not O-N-E. You see what I'm doing there? At no point are we dealing with the die result as a number. It's only a condition. We may as well spell it out. For all the difference it makes, it may as well have been a cube with different colors painted on the side. Happens to be numerals, 1, 2, 3, 4, 5, 6. But at no point in this process are we treating the 1 as a number. It is only a condition that results or fails to result, right? Success or failure. And the probability of getting this particular thing happening when you roll the die is 1/6, regardless of what it is the previous times. And you're going to do it 80 times. So the number of ones that you get has that probability distribution. What's the difference between B 3 comma 0.5 and B 80 comma 1/6? Well, the 50-50 split will give you a kind of symmetry that you don't have with the 1/6 5/6 split, but that's not what I mean. We can and have made charts where we have 4 columns, 0 or 1 or 2 or 3. But we're never going to make charts where you can have 81 columns. Theoretically, they exist. But again, you know, the difference between, where is it? The difference between this chart, the difference between this picture or chart and these pictures or charts should be obvious. You know, these we can create on our own. It may be tedious, but we can do it. This we're not going to be doing by hand anytime soon. On the other hand, look at it. It's predictable in a fundamental way that something like this is not. More on that as we go. Another example, well, some examples of things that are not binomial. Let's take it one at a time. You see there are 4 conditions here. If you really dig into it, there are 4 conditions. It may look like 3, but there's 4. You know how many times you're going to do something, call it n. Each is a success or failure. The probability of success is always the same. And you have to be talking about the number of successes. There's the hidden 4th condition. So let's look at an example. Let's look at various examples of things that are not binomial, where each of these conditions is violated. The average of 80 dice. You see, now we are treating them as numbers, not things that can be spelled out, O-N-E. Now, if you're talking about the average of 80 dice, then you don't have condition 2. You're not focused on each roll being a success or a failure. You're focused on the number on each roll, which you're going to add up and divide. So that's not an example of the success-failure situation. Another example, also not binomial. Number of flips to get ahead is not binomial. This violates condition 1. Flip a coin until you get ahead. How many flips does it take? Exactly what you don't have is a fixed number of observations, right? In fact, that's exactly the random thing. You don't know how many flips it will take to get ahead. So this is not an example of the binomial distribution. We're not going to talk about it in this course. This is an example of what they call the geometric distribution. It's another interesting type of distribution, but it's not one that we're talking about at the moment. What about condition 3? Pick 5 cards from a standard deck without putting them back. How many red cards do you get? That's not binomial because it violates condition 3. As we already saw back in section 4, at the very end there, there's a very big difference between picking 5 cards from a deck of 52 versus picking 5 cards from 100 decks all shuffled together, right? In the latter situation, taking 5 cards away doesn't really change too much the fact that half of them are red and half of them are black. But if you're taking 5 cards away from 52, you're taking almost 10% of the deck away. And if you get 4 red cards in a row, it's going to drastically cut down, noticeably cut down, your chance of getting a red card the next time. You can't really say that taking out red card after red card or red card is not affecting the probability of getting a red card the next time. You don't really have the independence. You don't really have the same probability. Now, if you put them back in shuffle after each pick, sure. What about the 4th condition? The proportion of heads in 100 flips. Flip a fair coin 100 times and talk about p hat, the proportion of flips that are heads. So, in other words, this guy can be 0 over 100, or 1 divided by 100, or 2 divided by 100, or 99 divided by 100, or 100 divided by 100. It can be 0, or 0.01, or 0.02, or 0.03, or 0.99, or 1. So it is true that we're going to flip the coin 100 times. What did I say, coin? Yes. It is true we're going to flip the coin 100 times. It is true that everyone is ahead or not ahead. It is true that the probability of a success is always ahead regardless of what's come before. But it is not true that you're talking about the number of successes. Now, as I said, you're only a unit change away from number of successes multiplied by 100. Or divide by 100, as the case may be. But you're not actually the number of successes. So this is very close. Only numbers of successes have the binomial situation, the binomial distribution, I should have said, binomial distribution. Proportions of successes do not have the binomial distribution. However, they are only a unit change away from something that is the binomial distribution. If you multiply by 100, that gets you back to number of heads, and that does have the binomial distribution. So it's not a actual binomial situation, but it is just a unit change away. So you see why I dwelled on that point up above? It's nice to know that if you understand one of these, you basically understand the other. Because one or the other of them might be easier to deal with, it's nice to know that it doesn't ultimately matter from a theoretical perspective. Oh, let's see. Large warehouse full of calculators, far more than we're going to pick out. 10% of them in the warehouse are defective. We'll choose a simple random sample of 15 calculators. How many defective calculators do you get? Well, it might be none of them, or one of them, or two of them, or 14 of them, or all of them. So yeah, we meet all those conditions. We know how many we're going to pick. Each of them is defective or not. The probability of getting a defective one is essentially 0.1 because what we're taking out is so small compared to hundreds of thousands of calculators in the warehouse. And we are talking about the number of the bad ones. So that's B15, 0.1. Note that many of our previous exercises, not all of them, note that many of our previous exercises in Section 5 fall into the binomial situation, and that we've worked out these charts for samples of size 1, 2, 3, 4. For a fair coin, we could even go to 5. After that, it gets to be real work. So we've talked about this. We talked about how this blue-eyed, which one is this? This is the blue eyes. So we've talked about how these various samples, 20% of people have blue eyes, pick out a few. It's binomial, how many, comma, 0.2, right? And we talked about the one that we went over in the video, which was the left-handedness, which were all binomial, however many, comma, 0.1. But a lot of the examples in the homework were as well. Let's see, 40% of students oppose student fees. Pick a sample of 3. How many oppose it? Well, long story short, and you did work this out longhand if you did the problems, which of course you did. So the number of students who oppose when you're picking 3, and every time you pick there's a 0.4 probability that they oppose, has the binomial 3, 0.4 distribution. Now again, if you're picking 3 from thousands of students, then effectively you've got a 0.4 chance of an oppose every time you pick. Oh, let's see, the marbles, I forget what this was, but without referring back to the previous Section 4 homework, I believe it was a 30% chance of a brown marble. Let's assume that it was. So that if you picked 4 marbles from a huge vat of millions of marbles, then the number of brown marbles that you get is going to be the binomial 4, 0.3 distribution. I'm assuming it was 0.3, but you can check that out. Let's see, the blood types. That I don't remember off the top of my head, but there you can check it out on the previous homework. There was a certain probability that they had type A blood, so when you pick 3 people from millions, binomial 3, whatever that probability was. Binomial 4, whatever that probability was. If memory serves, this was something like 27%, 0.27, and this was something easier, I forget what. This was not a binomial situation because nothing that we're doing here fits those conditions. Likewise, I just mentioned this one was not either. And I don't know why I put a space there, but this is one problem. These problems, while we're here, these problems in Section 5, they basically fall into about 3 types. Type 1, or where they have this binomial distribution. You're going to do something so many times, there's a certain probability of getting a yes. It's always the same. How many yeses do you get? That's the binomial situation. Then there are problems like 4 and 5, and 7, which are not the binomial situation. They're just more generic examples of using the probability rules to find those charts. And finally, there are problems like 6 and 7, where in so many words they are giving you the chart, and then just asking you to find the mean and standard deviation of it. And as always, these answer keys at the bottom here are kind of residual. They're nice PDFs that I have since created. I just didn't get around to deleting all of this stuff. So how to actually compute these? Well, we did it ourselves for samples of size 1, 2, 3, and 4. After that, it starts to get a little complicated, right? All failures, all successes, relatively easy to compute. One different from the others, relatively easy to compute. That middle column, if it's a sample of size 4, 0 or 4, 1 or 3, and then you do 2, you can do by the process of elimination, right? Because they've got to add up to 1. After that, they start to get complicated. After that, you start to get into this number of ways, number of sequences type of thing. And that takes us a little far afield for this course. So the bottom line is, how do we compute these binomial distributions? Well, there's a very short, elegant answer to that. We don't. We're not interested. But let's take it a little more slowly. The classical answer to this question is that we can use binomial tables. Now, these are never going to be complete, of course, but the classical example before calculators and such was that we could refer to binomial tables. You can Google up binomial tables if you're interested, but where are some of the examples that we did? This would be the brown marbles. Let's see, I know we did this one, right? I forget which one it was. It must have been the 4 left-handed people. So there was a 0.1 chance of people being left-handed. You were going to pick 4. And there they are. We did that one in the video, right? Probability of 0 left-handed people, of 1, of 2, of 3, of 4. And they've got to add up to 1. And so forth and so on. Or take something like flipping a fair coin 3 times. I know we did that one as well. So if it's a fair coin, then the probability of a head is 0.5. And if you're going to flip it 3 times, then the probability of getting 0 heads, or 1, or 2, or 3, well, it was 1/8, 3/8, 3/8, 1/8. We did it with fractions, but here they are, 1/8, 3/8, 3/8. 1/8, and sure enough they add up to 1. You could ignore this column over here. This is just doing number of failures, which is just a flip. We did talk about that briefly. Alternately, you could actually try to compute these, and good luck with that. This takes us a little bit far afield, but these can be actually computed. Now, my guess is that if you have a calculator that has a I couldn't swear to it, but 9 times out of 10, if you have a calculator that has a factorial button on it, you probably have a binomial, an actual compute binomial on your calculator anyway. But theoretically, if you did want to compute these by hand, well, first of all, you'd have to know what factorial is, and we don't really get into that in this course. 5 factorial, for instance, is 5 times 4 times 3 times 2 times 1, you may have seen. So suffice to say, these binomial distributions are very, very tedious to compute, and if you don't at least have a factorial button on your calculator and an exponent button on your calculator, your chance of computing these in any situation where you would ever actually need them is pretty slim. Now again, bear in mind that these fall into about 3 categories. We've got samples of size 1, 2, 3, 4, where it's not that hard to intuit our way through it. We did plenty of that in section 5. And then we've got samples of size 20, where it's still pretty jaggedy, 0 or 1 or 2 or 3 or 19 or 20, but a little too complicated to compute by hand. And then we've got things like samples of size 80, which is never going to happen by hand, and ironically, things get a little easier. And we'll talk about that. But the bottom line is, in a course like this, we're not going to be wanting to compute these by hand. Alternately, this being the 21st century, so they tell me, unless you subscribe to the phantom time hypothesis, you can just find these online, right? So Google up or Bing up binomial calculator, and probably the first thing that will come up is StatTrak. And this particular one is very nice. I don't think it gives you a great deal of decimal representations. Who's that, Tom Selleck? I guess it really is, huh? He's still alive, huh? Anyway, so by probability of success on a single trial, let's see, the left-handedness, right? So let's say 4 people who may or may not be left-handed. The probability, what am I doing? Probability of someone being left-handed, 0.1. I've obviously done this before. You may or may not be seeing these drop downs, actually. I forget how this works with the recorder. But probability somebody is left-handed, 0.1. How many people are you going to look at? 0.4. Number of successes, let's do 3. And then just hit calculate. And there it was. It was 0036, you may remember. Or let's go to one that we can physically call up on the screen, right? Let's see. So maybe this one. So a 0.2 chance that somebody has blue eyes. What's the probability that 3 people have blue eyes? It should be 0.256 according to this. This one is what I'm shooting for. So let's find out. Where did that go? Binomial calculator. So there was a 0.2 chance that somebody had blue eyes. I think it was still 4. And I think we're still interested in 3. Yes? So good to go. And do I have to blank these out, or are they going to correct themselves? Let's find out. There you go. 0.256. The probability of x being the specific number that you wanted, 3. 0.256. You could ignore the rest. So these can be just computed on. These can just be computed online. If you've got a TI type calculator, I do, but it's not within reach at the moment. Got it. So if you do have a TI type calculator, that's a TI type calculator, but it's not the one I wanted. Here it is. If you do have a TI type calculator and you're capable of getting it out with one hand, then you can just go to something like second distribution, scroll down until you find binomial PDF, binom PDF. On mine it's option 0 between 9 and A. And my wild guess is that it's going to want the sample size first. What are we working on? 4, followed by the probability of success, 0.2. So binom PDF 4, comma, 0.2, comma, and let's say we type in a 3, parenthesis, and it'll give me 0.256. Alternately, if you leave off these 3 and just type in binom PDF 4, comma, 0.2, then it'll give you with brackets. It'll scroll across and give you the whole thing. As I read it, 0.4096, 0.4096, 0.1536, 0256, 0016, which with any luck is exactly what I've got on the screen. Yes. So yeah, these TI type calculators can do these automatically. You can work them out manually. I mean, we're not going to do it in this course. It's incredibly tedious. Or, bottom line, we're not that interested, for reasons that we'll talk about below. Well, let's figure it out logically, right? Oh, let's see. Can I get rid of this damn update thing without turning off the video? I can. There you go. If I wanted to quit my job and update my browser full-time, I would do it. Oh, let's see. So, let's think this through logically. Remember, this is not a course in probability. This is a course in statistics. If you want to know what proportion of... This is all background information for going backwards in later sections, remember. It's very handy In order to know what you can reasonably conclude from the statistic you got, as I said in the past, you have to know the pattern of randomness for what that statistic was likely to be. And probability is always hard to talk about in the past tense, I'll give you that. So, but remember, this is all still background information. Understanding the probability of a statistic is still, understanding the probability distribution of a statistic, the pattern of randomness of a statistic is all still background information for practical stuff we want to do later. We are not interested in it in its own right necessarily. So although this is all very interesting, how practical is anything we've just been talking about? Well, the bottom line is, if you want to know what proportion of people in New York State are left-handed, you're not going to be picking a sample of size 4. You're not going to be picking a sample of size 20. You're not going to be picking anything where you could figure this out. You're going to be picking a sample of size 1,000, right? You're going to be picking a sample which is much more complicated. Too complicated to do any of this stuff, whether it's by hand or even in chart form. I mean, let's play devil's advocate here and say that we picked 4,000 people. Yeah, you see what I mean? The probability of exactly anything, certainly 3. Oh, let's see, what's 20% of 4,000? So the most likely individual possibility here would be 800. And I don't have high hopes for this either. You see, even the tallest bar is still very thin. Big deal, 0, 1 something. So that's as big as these get for a sample of size 4,000. You see what I mean? This is not a handy way of looking at this for large samples. 0 probability of 0, 1 probability of 1, 2 probability of 2, 4,000 probability of 4,000. The biggest this is ever going to get is 0.15 something. 4,001 numbers, all of which add up to 1. No particular one of them is going to be very big. It's not jaggedy at all, right? It's comparatively smooth. So obviously this is not very handy for large samples, and by the way, large samples are what we're always interested in the real world, right? So this is a curiosity. This binomial distribution is handy, well, actually computing it. It is still binomial, sample size 4,000 and all of that. It's just not a handy way of thinking about it. So all of this that we've just been talking about is a curiosity. It's a handy way of looking at things for smallish samples, 20, 30. Using these calculators would be handy when the sample size was 20 or 30. Too big to figure out on our own, but small enough to still be of interest. But as you've seen, for very large samples, patterns begin to kick in. You would think that the number of left-handed people when picking 1,000 people would be much more complicated than the number of left-handed people when you're picking 4. And you'd be right. A chart consisting of 1,001 numbers with 0.000 something underneath every single one of them is much more complicated than a chart with 5 bars, right? 0 or 1 or 2 or 3 or 4. Thought of as individual possibilities, 1,001 bars or 1,001 columns is much more complicated than a chart with 5 bars or 5 columns. But it's also true that we're far less interested in individual possibilities. And this gets us back, unless I idiotically closed it. Here it is. Oh, I wanted that actually. You see, you notice the difference between small sample sizes. Jaggedy, bar bar, jaggedy, bar bar bar, jaggedy, bar 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 bar, jaggedy, bar 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 bar. Well, you know, theoretically jaggedy, it happens to be a tie. You notice the difference when you get to large samples. And this is not perfect because there are limitations in the program I'm using to generate this, but you get the point. It's a lot smoother. And this is only 80, by the way, which is still not great in the real world. 1,000, maybe. So you take my point, it's enough to see what I'm doing here, which is that at some point, as the sample sizes get bigger, at some point the shape becomes more important than the individual bars. At some point the bars become negligible. Less than 2, at most 2. The presence or absence of this bar makes a bit of a difference. Less than 19, at most 19. Well, the presence or absence of this bar doesn't make too awful much of a difference, right? And this is only 80. It's still too small to be of any practical use. So at some point, the patterns become more important than the individual bars as sample sizes get larger. And again, remember, there's all kinds of reasons why large samples are more practical than small samples. Number 1, common sense. Number 2, the principle that we ended with in section 7, large sample, less variability. So notice the difference between the jaggedy pictures for small n and the smoothish pictures for large n. For small n, we add up individual possibilities. You want to know what's the probability when you pick 20 people that less than 6 of them are left-handed? Add up the probabilities, 0 or 1 or 2 or 3 or 4 or 5. You want to know the probability that when you pick 1,000 people, that less than 99 of them are left-handed? Well, theoretically, you add them up, 0 or 1 or 2 or 3 or 98 or 99, all those probabilities. But not really, right? You're not going to add up 100 numbers. Shortcuts kick in, and you can see the shortcuts kicking in. As things become smooth-ish, we can think of them as density curves. Section 3, we can use area to compute probability, which you can't really do for jaggedy bar, 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 bar. So this is why it's important that when you have, say, 2,500 people, yeah, it is technically a discrete distribution, and if you wanted to know the probability that less than 1,400 people like action movies, you would add up the probabilities for all 1,401 of these. But no, not really, because you can do it as a continuous random variable and use areas. You don't want to have to be adding together hundreds of numbers that are all 0.000 something, right? It's meaningless, tedious, and rounding error is bound to creep in. It's a non-starter. Yeah, with computers, sure. But even computers are going to have their limitations here because those factorials get unwieldy very, very big. I got rid of the formula. But even computers are going to have trouble with some of those numbers without rounding, without having errors. Obviously, in the real world, we're interested in very large samples, like I said. So for practical statistics, the actual binomial calculations are not that important. Let's recap. If you flip a coin 3,000 times, then the number of heads is going to be B 3,000, 0.5. True statement, but also kind of irrelevant, because thinking of it as 3,001 bars is not very conducive. It's not a handy way of thinking about it. And the picture becomes so familiar that shortcuts kick in. This is the irony. The larger the sample, the more predictable everything is. And because things are predictable, shortcuts kick in. So that means that ironically, the larger samples are a lot easier to deal with than the smaller samples. Think about what a chart would look like if you had a sample of size 20, 21 bars. That's relatively complicated. On the other hand, look at what it looks like when you've got 80 bars. Well, first of all, you don't have 80 bars here, right? Most of them are so invisible that they're not even being pictured. Only the ones from, 5 to 30 are big enough to even be visible here. Although theoretically, there are 81 bars whose heights are, so close to 0 that we just didn't bother. The picture, the smoothness, the shape kicks in. 21 bars would be nasty to think about. 81 bars, ironically, is relatively easy to think about because it becomes so smooth that shortcuts kick in. This is not smooth. 21 bars would still not be particularly smooth. It would have the disadvantage that it would be a lot more complicated than this to compute, on the one hand, but also the disadvantage that it wasn't big enough for the shortcuts to kick in. On the other hand, you're never going to pick a sample in the real world of size 20, right? So for practical statistics, when we actually go on to the sections where we're going to be using this stuff, the binomial is not that important. The binomial way of looking at things is just not that important. It's important from a theoretical perspective to understand the basic ideas in play, but when it comes time to compute these, we're never going to actually be computing them as binomial variables. Beyond the curiosities that we did in section 5, how many people have blue eyes when you pick 4? Because samples of size 4 we can still deal with without getting too messed up in the formulas here. Samples of size 10, that's starting to get complicated. Samples of size 1,000, well, ironically, that's starting to get easy again, but we haven't quite talked about how yet. So we're at an hour. Coming up on 1 hour and 1 minute. This seems like a good place to stop this. I will end on this note. Every random variable, including these binomial ones, has a mean and a standard deviation. So next up we want to talk about the mean and standard deviation of binomial variables. And then we'll be starting to get back to what's practical. If you're thinking ahead toward, where we're going with this, look at it. You can probably see where knowing the mean and standard deviation in a situation like this could be immensely helpful. And I think I mentioned that before. Every random variable has a mean and a standard deviation, but them being useful is a whole other situation. So we did mention that at the end of section 5 and in section 6. So this is a good place to stop this video. And we'll pick it up with part 2 next time. I think we can probably get away with 2 parts in this video, but we'll see how it goes. When I upload it, I'm going to call it 1 of 2, but I may have to change that later.